An interesting application of partial pressure in Dalton's law is when we can use mole fractions to figure out partial pressures. In general, we said that the total, you can write an ideal gas law as long as you apply the total number of moles, RT, VT, or you can apply your own in a mixture. For example, in the problem that we will solve, there's helium and oxygen, so the pressure of oxygen is equal, the partial pressure of oxygen is equal to the number of moles of oxygen, RT, divided by volume. There is another way to solve this, and as we talked about fraction, in this case, we're gonna refer the fraction as the fraction of oxygen will be moles of oxygen divided by the total number of moles. Therefore, the fraction of helium is the mole of helium divided by the total number of moles. Of course, the total number of moles is the number of moles of oxygen and the number of moles of helium. Okay. The interesting thing of using just fractions, and notice that it has to be a value between 0 and 1. It's not a percent, it's a fraction of 1. You can see that the partial pressure of oxygen will be the fraction of oxygen times the total pressure. Okay, and the partial pressure of helium will be the fraction of helium times the total pressure. So it's fairly easy to see that this holds true, because what this contains in here is just the nRT over V that for that specific component, in this case for oxygen. Okay, we're not going to show that where we got these numbers from, but it's not a very difficult demonstration. Okay, in this case, it's asking for find the mole fractions and partial pressures in a 12.5. So let's write a container. The volume is 12.5 liters. Okay, and the temperature, this is the volume. It's important to write down and to draw something so that you keep a visual record of what the problem gives you and what it's asking. In this case, it's asking for the mole fractions, and it's asking also for the partial pressures. All right. Notice that we're given volume and temperature, and we're given the grams. So first, you cannot use PV equals nRT using grams. You need to move it into moles. In here, you would put the atomic weight of helium, grams. It would be 1 mole, and for oxygen, 4.32 grams of oxygen. You would put the molecular weight, which I believe in this case, now I remember it off the top of my head. This would be moles of helium, this would be moles of oxygen, and that's a number that we know. Okay, notice that from here we can calculate the total number of moles. Total number of moles will be total helium plus the moles of oxygen, and therefore we can calculate the fraction of oxygen, and we can calculate the fraction of helium by using these equations up here. All right. So we have the total number of moles. We are able to calculate the fractions. Can we calculate the total pressure? The total pressure would be the total number of moles times R, which is 0.002 atmosphere, liter, mole, and Kelvin. I will not get tired to write all of the units. It's important so that you see that they all cancel out. The pressure, the temperature is 298 Kelvin, and the volume is 12.5 liters. Okay, notice that we have calculated the number of moles, therefore we can calculate the total pressure. What is the partial pressure? Well, in that case, the partial pressure, we have calculated the fractions, we have calculated the total pressure, we can calculate the partial pressure of each of the component in this mixture. Hopefully this makes some sense. I prefer to leave the problem as is without actually introducing the numbers, so that you can see a little bit the procedure. The moment we start plugging in numbers into a calculator, I believe that we kind of lose track of the whole strategy. Hopefully all of you are capable of calculating all these moles, adding them up, plugging it in here, and then therefore calculating the partial pressure.